All right, guys, we're on to Unit 8. So Unit 8 is all about acids and bases. So first of all, we want to kind of remember acids and bases, what they are. So we generally, in AP here, we talk about Bronsted-Lowry acids and bases. An acid, of course, is a proton donor, and a base would be a proton acceptor. So proton donor, right, we generally think about something that is going to release H plus or H3O plus, right, if we are in water. So an example of this would be HCl plus H2O, right? We're diluting HCl in water. We're going to form H3O plus and Cl minus, right? So it is a proton donor. That would be our acid there, okay? Bases, right? We think of acceptors. We oftentimes think of OH minus, but we could have something like NH3 plus H2O, right? NH3 is going to accept that proton and become NH4 plus and OH minus, okay? So those would be an acid reaction and a base reaction, right? Acid, HCl, base, NH3. But whenever we have an acid and a base reaction, we always talk about the conjugate acids and pairs, right? So we would have here an acid. H2O is a base because it is going to accept that H plus right now, right? So the conjugate acid of H2O would be H3O plus. This is a pair, all right? And then HCl is the acid. The conjugate base would be Cl minus, okay? So we want to be able to identify the acid, the base, the conjugate acid, the conjugate base, and those pairs, okay? So then if we look at this one, right, NH3 here is going to be accepting that proton, so that would be a base. Its pair, the conjugate acid, would be NH4 plus. And so then H2O here is going to be the acid. It's going to lose H plus. OH minus would be the conjugate base. Okay? Okay, so we should be able to take our reactions, identify the acids, the bases, conjugate acid, conjugate base, and the pairs with them, okay? So then if we start talking about our acids and bases in water, right, turns out that water, right, is in equilibrium here with acids and bases, okay? So if we think of, whoops, H3O, oh my gosh, I'm going to rewrite it here. H3O plus OH minus in equilibrium with two H2Os, right? That is our equilibrium with acids and bases in water, okay? We could alternatively write it the opposite way, which is kind of our more common way. So 2H2O in equilibrium, it can split up essentially. We can form H3O plus and OH minus, right? What happens to water? Well, we have this equilibrium. So if we have an equilibrium, of course, we can write the equilibrium constant. Well, the equilibrium expression would be K. We're going to substitute it as KW. And that equals, well, products over reactants. Reactants aren't going to be in there, so it's just going to be the products here. So concentration of H3O plus times concentration of OH minus. Okay, so KW, that's right over here, is the equilibrium expression for water, right? And with water, it is 1 times 10 to the minus 14th at 25 degrees Celsius, okay? So if we have pure water at 25 degrees, right, we're going to have the same ratio, or sorry, the same concentration of H plus and OH minus, okay? And so in pure water, it's going to be 1 times 10 to the minus 7th molar, This would be a neutral solution. If we have a neutral solution, right, we always are going to have the H plus concentration equal to our OH minus concentration. That does not mean that we always have 1 times 10 to the minus 7th molar, okay? We're going to talk about how the Kw changes with heat. We know this, right, with an endothermic or an exothermic reaction, okay? So this concentration is only valid if we have pure water, a neutral solution at 25 degrees C. But this relationship, where our H plus is equal to our OH minus, is going to be true no matter what if we have a pure neutral solution, okay? But then let's talk about an acidic solution. If we have an acidic solution, right, that means that we have more H plus, right? So the H plus concentration is going to be greater than 1 times 10 to the minus 7th and is going to be greater than the OH minus concentration, okay? Again, these concentrations at 25 degrees C, okay? Basic solution, right, our OH minus concentration now is greater than our H plus concentration, okay? So if we know H plus concentration, we should be able to calculate the OH minus concentration, right? So Kw is 1.0 times 10 to the minus 14th mole, and that equals, well, our H plus concentration is 5.0 times 10 to the minus 9th molar times the OH minus concentration. So we solve for the OH minus concentration, and I think OH minus concentration equals 2 times 10 to the minus 6th, okay? So that's just rearranging and solving for our variable, okay? So then, because these times 10 to the minus 14th times 10 to the minus 9th, right, these are kind of inconvenient, we came up with the pH and the pOH scale, right? This is a logarithmic scale. So the pH, right, is equal to negative log the concentration of H3O plus, okay? H3O plus or H plus, again, if we are in water, H3O plus concentration is the H plus concentration, okay? So then the pOH, right, this would be negative log of the concentration of the OH ion, okay? So then, again, if we have neutral water, right, we think about neutral water, well, the pH, right, we said pH is negative log of the H plus concentration. Well, if we have neutral water at 25 degrees Celsius, our neutral water has a H plus concentration of 1 times 10 to the minus 7th. So 1 times 10 to the minus 7th. If you do that calculation, our pH equals 7, right? But it will change, again, with the temperature, okay? So then, right, we have pKw, right, which is, again, the negative log of the Kw value. So the pKw, negative log of pKw, is going to be equal to 14. So 14 has to equal our pH plus our pOH, okay? So these are all just kind of mathematical relationships. Last year we used the square, right, where we had pH going back and forth to pOH. That can go up to or back to our OH minus concentration. We can go in between our OH minus concentration and our H plus concentration. We have that square that we can go all the way in between, right? So if we're going between pH, H plus, right, we're taking the negative log, or if we're solving this the opposite way, right, it would be 10 to the negative pH. That's going to give us the H plus concentration, right? If we're going from pOH to OH minus, same idea, right? If we're going pH to pOH, we've got 14 equals pH plus pOH, and then we have the relationship up here, right? That is all coming from our Kw, right? The equilibrium expression. Okay? Whew! All right. So then, if we have an acidic solution, pH is going to be less than 7, again, at 25 degrees C. If we have a basic solution, the pH is going to be greater than 7, okay? Again, pH is not pOH. It gets confusing. We got to make sure that we keep these things separate in our minds, okay? Okay, so let's do a couple of problems real quick, easy here. If H plus concentration equals 2.4 times 10 to the minus 6 molar, calculate pH. Well, pH equals negative log of our concentration, 2.4 times 10 to the minus 6th. We plug that in. That should be 5.62. Okay. Suppose pH equals 8.68. Well, let's calculate H plus. Well, H plus concentration, right, is going to be, so H plus concentration equals 10 to the negative pH. So 10 to the negative 8.68. That equals 2.09 times 10 to the minus 9th. Now, you notice, right, pH between 8 and 9 there, right? We go up to negative 9th, right? This is a way for us to estimate, okay? If we know, well, this is 10 to the negative 6, well, I'm going to estimate that the pH is going to be between 5 and 6. That's what it is, okay? So we do need to start getting good at estimating, because that might be something that could be useful for us, okay? All right, we'll be back in a second.